Now, so hello and good afternoon, everyone. There's a question. There isn't a lecture next Thursday, right? Next Thursday, I think it's Christi Himmelfahrt in German, Ascension Day. So I think here in Saarland, that's an official holiday. So no lectures on official holidays. That's correct. Okay, good. Now, at the end of today's lecture, we're doing a quick quiz again. So be ready or prepare yourself to start the quiz at 1:45. So the quiz is gonna start at 1:45, and you have time until 2:10. So there's plenty of time. So for this quiz that our tutors prepared. Whoa, that was loud. For this quiz, you should have a maybe a calculator next to you. So there it might be useful to have a calculator ready for this quiz. It's just a tiny computation thing, but just to warn you, maybe have a calculator ready. Okay, good. Let's get started with today's lecture. All right. Good. Last time we stopped at this slide. Where we defined what it means for an encryption scheme to be perfectly secret, and this is a sort of a modern version of Shannon's original definition, which essentially says that the distribution of the message should be independent of the distribution of ciphertexts, or vice versa. That means the same thing. So the distribution of ciphertexts independent of the distributions of message. And now, of course, for ciphertexts to be random, we need a random key, right? But the key comes out of our keygen algorithm. It's chosen randomly by our keygen algorithm. So now that we have a definition of perfect secrecy for an encryption scheme, let's go right into it and look at an encryption scheme which is perfectly secret. So for this scheme, the keys, take maybe blue, key space, message space, and ciphertext space are all binary strings of length n. And really, if you want to have it super simple, just think of n equals 1. Their keys are just bits, messages are bits, and ciphertexts are bits. But in general, we'll do this for binary strings instead of just single bits. Okay, key generation is fairly simple. So we, as a key k, we just choose a uniformly random key k and output this key. That's our key. To encrypt a message m in our message space, which is of course 0, 1 to the n, with a key k, we just compute the bitwise XOR, the bitwise exclusive OR of the key string and the message string. And now, of course, who wants it a bit mathier, the bitwise XOR is just the sum of these two bits, and you reduce the result modulo 2. So bitwise XOR is addition modulo 2. Okay, that's encryption, fairly simple. Just take the message and sort of shift each bit of the message either by 0 or 1 and reduce it modulo 2, depending on what the key is. And decryption does precisely the same thing as encryption. So to decrypt a ciphertext C, we just XOR the key K on top of this ciphertext C. Okay, that's our encryption scheme. That's our one-time pad. What's the first thing we should check that this scheme fulfills? What's the first property we should establish for an encryption scheme? Anyone? Just a quick comment. Correctness, precisely. Exactly, decryptions of the cipher yields the correct message. So let's do that. Let's look whether this scheme is correct. So let's look at correctness. For that, we just take ourselves, we fix the key K in 0, 1 to the N, a message M in 0, 1 to the N. And now let's look at what is decrypt using key K of encrypt using the same key K of M. Well, this is just, let's maybe write it like this, decrypt K of, if we now plug in encryption, that's just K XOR M. But now if we plug in the definition for decryption, we just get K XOR K XOR M. And what is that? What happens if I XOR K onto itself? What is K XOR K? This is the all zero string, exactly. It's just, let's write it 0 to the N. And if we XOR 0 to the N on something, nothing happens. So this is just M again. So we have established that the one-time pad is correct. Really, encryption and decryption do the same thing and are, as we have seen here, just in inverses of one another. So they're the same thing and they're inverses. Mathematically, we call something like that an involution. That's a function that is self-inverse. So encryption of for the one-time pad is self-inverse. Okay, so this is this was correctness, but what what about secrecy? What do we have to show for? What do we have to show for secrecy? Well, we need to show that for any distribution of messages n, for any distribution m of messages, and of course a uniformly random key and a uniformly random key K, which we pick from 0, 1 to the N. It holds that M and enc K M are independent. Good. So how do we do this? Well, first, we fix any distribution or random variable distribution. I'm using this synonymously, distribution M of messages. This is a random variable, right? So M is a random variable which somehow generates messages randomly. I'm not going into detail how M does this, but M is any distribution of messages. That's what the security definition requires, that no matter what the distribution of messages is, messages and ciphertext should still be independent. Okay, so in the end, what we want to show, let's maybe make that in red, to show, right, is that the probability of m equals m, given that enc k comma m equals c, is the same as probability m equals m for any m in M and C in C. All right, so let's do this. So we have to show that this equation here holds. So let's start with the left side. So we have probability M equals M given enc k comma m equals C. Well, that's not so easy to work with, right? Now on the what we condition on is an expression that depends on the ciphertext, and the ciphertext is a function of m, whereas we have m on the left side. So to make our life easier, let's just turn this around and move enc or the ciphertext to the left side and the message to the right side. And how we do this, of course, is via Bayes. So how do we do this? Well, let's just plug in Bayes' law, and this then just says that oops. This is the same as, oh, by the way, before I do this, it's maybe easier to just plug in again the definition of the encryption algorithm. But there's questions. So someone asks, would it suffice to argue that a random key is equivalent of flipping random bits, and thus it comes down to guess the key? I mean, what we want to show is what we want to show in the end is this equation here. So why do we have enc km and not enc km little m? I mean, this is the ciphertexts follow this distribution, right? If we go back for a moment to the definition of perfect secrecy, right? It says for all messages lowercase m and all ciphertexts c. Exactly. So m, someone answered this already. M is the random variable. Capital M is the random variable, and lowercase m is the message. Good. Thanks. Thanks for helping me out with the comments here. So, whoops, let's just plug in our definition of encryption, right? This is just kx or m equals c. And now to flip this around via Bayes, this is just probability kx or m equals c conditioned on m equals m times, well, we still have our probability m equals m divided by probability kx or m equals c. That's just Bayes' law. Okay, but now let's first have a look at this probability here. So the probability that kx or capital M equals c, given that capital M equals m. So if we condition on capital M equals M, then of course, also on the left side in this probability here, we can replace capital M with lowercase m, right? So we condition on M being always the same value, lowercase m. So we can simplify the expression on the left side, equals C given M equals M. But now we let's maybe rewrite this one step further. This condition here, Kx or M equals C, this is of course equivalent to K equals Cx or M given M equals M, right? Because in this expression, I can just X or M on both sides. Then on the left side, it cancels out, and I have simplified things a bit. But now I know that keys and cipher keys and messages are chosen independently, right? So the key is chosen uniformly at random and of course independent of the message. So this once more simplifies to probability K equals Cx or M, because M and K are independent. Now, the key is chosen uniformly random from 0, 1 to the n. So the probability of the key, assuming any fixed value, Cx or M is a fixed value, is just 1 over 2 to the n, because K is chosen uniformly at random from the set of strings of length n, and there's 2 to the n, many of them, right? So each one of these strings has probability 1 over 2 to the n. Okay, so good. If we look at this now, we have computed this term. Can I have maybe a pointer? Can't really point. So we have computed the first expression here. In the end, we want that that we're just left with probability M equals M. So for what we have to show for that is that this term here is also 1 over 2 to the n. And let's go there. So maybe let's start with blue. So what is probability Kx or M equals C, right? This is what I've just underlined in green. Here we're going to write out this term. And what we're going to do here is we have now 2 random variables, sort of a system which depends on 2 random variables. Well, what can we do with this? Formally, well, one thing we can do is just go over all possible choices of a message. Let's call it M prime in M, which is 0, 1 to the n, and use the law of total probability, right? The law of total probability lets us disentangle such a probability that depends on several random variables into things that depend on simpler random variables. And let's see how we do this here. This is just probability Kx or M equals C, the same as still here. But now we're conditioning on M equals M prime. And have this times probability M equals M prime. This is just the law of total probability. And as we've seen on the last slide, when we condition on M equals M prime, we can just substitute this capital M on the left side with M prime. So this probability is just Kx or M prime equals C, conditioned on M equals M prime. But now we know that K and M are independent. So this is really just probability K equals C XOR M prime, right? But we still know that K is just distributed uniformly random over 0, 1 to the n. So also this probability here is 1 over 2 to the n. And what we're left with is, well, this probability, let's write it out, 1 over 2 to the n times probability m equals m prime, where we're summing over all m prime in M. Here we can pull out the 1 over 2 to the n from this sum, and we're just left with m prime in M. Probability m equals m prime. What's this? What is this sum? 1, exactly. So we're summing over all possible choices for m prime. So we're covering the entire space, and one of them must be the case. So this probability is just, oops. This is just equals 1. So we have 1 over 2 to the n. And consequently, if we plug things in from the last slide, we have probability m equals m, condition on k XOR m, or let's leave it with the encryption here, enc k comma m equals c is just 1 over 2 to the n times probability m equals m divided by 1 over 2 to the n, which is just probability m equals m. And we're good. That's what we had to show. Now we've shown that the distributions of messages and ciphertexts are independent. Okay. There's question. How do you know? No, first the first question is. I'm sorry. Can you explain how it won? I guess you want to say how it is one. So these events, m equals m prime, that's an exhaustive set of events, right? You can write this probability as just via the union rule as probability. Let's say here we have union m element, the message space, and the events that you have is m prime, m equals m prime, right? And these events m equals m prime, they cover the space of all possibilities, right? The random variable m needs to output something. So this statement in here, excuse me, is just true. And probability of true is 1. So, sorry. How do you know, another question, how do you know that m and k are independent? Is this an assumption or a given? This is a given. Did we, let's maybe scroll back. Here, the perfect secrecy. So good. So we here we choose k via the key generation algorithm, and I mean, the way I wrote it here, k is chosen after m and uniformly at random. That means m cannot depend on k, right? So yes, from this it follows that k and m have to be independent, which they are. Okay, good. There's more questions. the question is, this generalizes to any modular addition on the alphabet of message. Is that correct? E.g. Vigenère cipher with an infinite key. I mean, I don't know what you mean with an infinite key, but yes, in fact, the one-time pad generalizes to any abelian group, or more generally to any group. It doesn't even have to be abelian, so you don't have to be able to switch operations around. So the one-time pad holds over any, let's say, finite group. Okay, good. Okay. Good. Let's go on. There's one more question. Isn't M the random variable and not the sample space? This calligraphy M is the space, the message space, and capital M here is the random variable. So those are different. Okay. Good. So let's get going. Why is this called one-time pad? Well, under sort of this name, it was invented in 1917 by Vernam. And the security proof that we just saw is just a variant of Shannon that was provided in 1949. So really until 1949, we didn't have a security model, or we didn't have a definition of what it means for a cipher to be secure. Shannon provided a security definition, the one we saw, perfect secrecy, and showed that the one-time pad meets this definition. Okay, but really, if we look at this proof, the security proof or security only holds if the key is used at most once. If you were to give me two ciphertexts that are encrypted with the same key, this proof wouldn't hold anymore. And if the key would be reused, this would in essence be a Vigenère cipher on a binary alphabet, right? So that's another indicator why Vigenère probably isn't secure. It's a simple operation, and we see the one-time pad is secure if you use a key just once and then throw it away. But Vigenère tries to reuse the key. There's a question: one-time pad is vulnerable to chosen plaintext attacks? Yes. If you give, so in the for the one-time pad, if you give me any message ciphertext pair, then you can directly compute the key. I mean, this is a simple exercise, but let's take the bottom line of this. We can use keys only once. That is, once we've used the key, we need to throw it away, and that means the one-time pad actually consumes large amounts of key material. That is, if, let's say, I want to communicate to any one of you 1 GB of information securely using the one-time pad, before we can do that, we have to make sure that both you and I have the same key, which is also of size 1 GB, right? And after I've sent this message, the key would be consumed and couldn't be used anymore. Once the key is used, it cannot be used to encrypt any other message. Of course, then a natural question is, can we do better? Is this a necessary thing that keys are as big as the messages we encrypt and can only be used once? And spoiler, yes, we're going to see how to do better in the course of this class, but not today. Good. Now let's briefly discuss our definition of perfect secrecy or perfect security. I'm using these two notions interchangeably. So when I say perfect security, I mean perfect secrecy. I see there's one additional question. Once a key of length n is used, does it mean that keys with length n cannot be used, or k is no more a random variable? I mean, a random variable is a way how you model a thing. Once you've chosen a key from a distribution, you're getting a fixed string, right? In the real world, you always have fixed strings. Think of random variables as processes that generate messages or generate keys, right? In our case, keys are generated by the keygen algorithm. So this algorithm specifies the random variable, which for the one-time pad was just chosen uniformly random. Good. Now, this definition that we've seen, namely that we ask that for any distribution of messages, message, comma, and ciphertext are independent, is actually not easy to work with. So it's a fairly intuitive definition of security, saying, well, if those two things are independent, then the ciphertext cannot reveal anything about the message. But really, it's not easy to work with if you were to design larger protocols. More importantly for us, this definition really seems not to generalize to weaker notions of security that will allow for more efficient schemes. So asking that two things are independent, that's nice and good for perfect secrecy and for the one-time pad, but it doesn't show us where to go from there. Okay. Good. What we're going to do now is we're going to discuss alternative approaches to defining perfect secrecy. So what we've seen in one of the lectures on historical ciphers was that it seems to be sufficient to distinguish if a message, if a ciphertext encrypts a message 1 or a message 2 to break this cipher, right? If you can learn whether my ciphertext encrypts the message attack or defend, that's already very bad. We want to avoid this at all costs. So what we're going to do now is we're going to take this idea that sort of for any pair of messages, ciphertexts should have the same distribution as our starting point. So we'll now provide an alternative definition of perfect security where, let's say, our adversary knows that the ciphertext encrypts 1 out of 2 messages. Think of attack versus defend. And he tries to learn which one of these 2 messages a given ciphertext encrypts. And of course, one can ask, is this a minimal attack goal? Are we, when we say that now we're trying to define security in this way, is this a good definition, or could there be other attacks, right? If this is not a minimal attack goal, then there could be other attacks that sort of don't manage to do such a distinguishing attack, but still learn something about the encrypted plaintext. So let's make this second definition a bit more formal. Our second definition of perfect secrecy says that an encryption scheme, keygen EncDEC, is perfectly secret if for all pairs of messages, M and M prime in the message space, and all ciphertext C it holds that the probability that if I encrypt M and get C over of course a key that's been chosen by the key generator, and the probability that if I encrypt M prime and get C are the same. Okay, so really what this what this definition now says is, no matter what M, what my message M is, the probability that a ciphertext is C is the same for all M, right? No matter what M you start with, if you start from M, M prime, or anything else, this immediately generalizes, then the probability that your ciphertext is C just doesn't depend on the message M, on what the message lowercase m is. And this notion somehow captures this idea of distinguishing attacks, right? If you think back about the Enigma, we knew that, for instance, that the letter E or any letter cannot map onto itself, right? So if you see a ciphertext and you know that, and you see the letter E appearing in a certain position, then you know any message M which has the letter E in the same position as the ciphertext couldn't have been the plain text. Right, so this probability would be 0, and for another message M prime, this probability could be non-zero. So this definition of perfect secrecy would definitely immediately make Enigma insecure, which is a good thing, right? Because we know Enigma is not, shouldn't be considered secure. So with this definition, the length of M does not matter anymore. It does. So the length of M, I mean, we once specified this message space M, and for the one-time pad, this was just 0, 1 to the end. So the length is sort of included in the definition of this message space. All right. That's our definition too. So the definitions we've seen here, right? Definition 1 and 2 are so far only concerned with the distributions of messages and ciphertext. Definition 1 was concerned with distributions of both messages and ciphertext, namely they should be independent. Definition 2 was basically just concerned with distributions of ciphertext, namely for every fixed ciphertext M, the distribution of ciphertext, sorry, for any fixed message lowercase m, the distribution of ciphertext should be the same. Now, in the end, who we want to defend against with encryption schemes is an adversary. But neither of these definitions make an adversary explicit, right? The idea that an adversary tries to learn something from a ciphertext only comes in if we know the context of what we're doing, that we're actually trying to show that some encryption scheme is secure. So there's no actual mentioning of an adversary in these definitions. So if I didn't explain to you that this seems to be sort of a minimal attack to distinguish encryptions of two messages, you wouldn't even know what that really has to do with an adversary who's trying to break the scheme. This question, and it says, in the def, both M and M prime are encrypted to the same C. That's not what it says. So enc km is a random variable. Because k is a random variable, then a then for any fixed m, enc km is a random variable. And this is just the probability that this random variable, namely a ciphertext of either m on the left side and prime on the right side, assumes a certain value, namely c. So already looking ahead, in the upcoming lecture, we want to study security notions against adversaries with different resources, different computational resources. So right now, again, the adversary is still super cloudy. We just say these distributions should be the same and therefore scheme secure, but we're not getting really a feeling of how an adversary could potentially interact with this encryption scheme or with this ciphertext. And that's why in our third attempt at defining security of perfect secrecy, we will make the adversary explicit. So here's definition 3. Again, keygen enc dec should be an encryption scheme. Quick break. And now A is which we'll call the adversary. We will always write it with this calligraphy capital A character, is a possibly unbounded randomized algorithm. So this algorithm is allowed to consume randomness, and we call it the adversary. So the adversary, that's an important takeaway from this slide. The adversary in cryptographic modelings is typically always an algorithm, right? An algorithm which tries to break something. You shouldn't think of the adversary as a person. We just give the algorithm, we just call this algorithm the adversary. Okay, there's a question. What does unbounded mean in this context? So I think you have taken courses or beginners courses in computational complexity or theoretical computer science. An unbounded algorithm is computationally unbounded. It can compute for as long as it wants. So in particular, it doesn't necessarily have to be an efficient algorithm. My algorithm A can be inefficient. It can run for exponential time, for double exponential time. Heck, I'll even allow this algorithm to solve, to have somehow a magic solver for incomputable problems, for uncomputable problems, such as the halting problems. Give this adversary a halting oracle. So when I say that something is computationally unbounded, it can so there's the next question. Basically, it can brute force anything. This algorithm can brute force through anything it wants to. It's not bounded by any time constraints. It can, again, do its thing for however long it wants. Good. Now we've fixed the adversary, and please always keep in mind the adversary is an algorithm. It's not some kind of magic box where the NSA or whoever sits inside think of it as an algorithm. An algorithm you can potentially implement in your favorite language like Python or C or you name it. Now, once we've fixed an adversary, we look at the following experiment. So I typically write algorithms as these boxes, and for the adversary, I like to use a red box. And now this adversary interacts with a challenger in an experiment. And the task of the challenger is essentially to test if the adversary can really break an encryption scheme. So think of this now as an interactive test by which the adversary can convince the challenger that he can actually break the encryption scheme. So what happens? Now, first, before anything happens, I'm allowing my adversary to choose two messages, M0 and M1. That's of his choice, right? So the adversary gives these two messages to the challenger or experimenter, however you want to call it. Now the challenger does the following thing. First, it generates a key, and then it flips a random coin B. So it chooses a bit uniformly at random, everything in secret. The challenger does this all in a way that the adversary doesn't see. So I would kind of covers himself up, flips a coin, something comes out, and also the key is hidden from the adversary. And now it encrypts the message MB. So if B is 0, it encrypts M0. If B is 1, it encrypts M1 under the key K and gets a ciphertext C star. The ciphertext C star will appear quite often in this course. We call it the challenge ciphertext. So the challenger computes a challenge ciphertext C star and sends it to the adversary. Now, what could we ask the adversary to do? Obviously, the adversary knows what M0 is, knows what M1 is. What could we ask of the adversary? Exactly. So the adversary should now tell us whether M0 or M1 was encrypted. And he can do that by providing a guess B, right? So the only information hidden from the adversary besides the key, but we're not trying to protect the key, we're trying to protect the encrypted message, is the bit B. So we're asking the adversary to give us a guess B prime for the bit B. And now the challenger says, if B prime equals B, then I output 1, meaning the adversary wins, otherwise output 0. All right, so we call this we call this the ciphertext indistinguishability experiment, right? Because in this experiment, we can test whether an adversary can distinguish encryptions of M0 from encryptions of M1, where M0 and M1 are even chosen by the adversary himself. And now for a given adversary and this stuff that this challenger does, we just define a random variable int A, which just describes the output of the challenger at the end of this experiment. So this is this int A is sort of quite a complicated random variable. We have to run this entire experiment here to get a sample from this int A. There's a question. Why is the key not chosen uniformly at random? I mean, the key is just chosen by the keygen. For the one-time pad, keygen just chooses the key uniformly at random, but other encryption schemes might have other distributions of keys. So this definition, we're not just, or these definitions, we're not just providing them for the one-time pad, but for encryption in general, right? So security definitions typically speak about all possible or a whole range of encryption schemes, not just a single one. Good. There's a question, when do we say a scheme is secure with this? That's a very good question. Now that we've defined this experiment and this random variable int A, we say an encryption scheme is perfectly secret if it holds for every adversary A. So for every unbounded algorithm that I can plug into this experiment, that the probability that the experiment outputs 1 in the end is exactly 1/2. So if the experiment outputs 1, we also say the adversary wins. So the winning probability of the adversary should be exactly 1/2. And the probability, of course, is taken over all random choices in the experiment. That means random coins that are used by the adversary, the random coins used for the key generation, and the bit B. Why not smaller equal 1/2? I mean, smaller equal 1/2 is less restrictive than asking equals 1/2. There's another question. What if it's still deterministic in a weird way, as if the adversary always has 1 after 0 after 1 after 0? Sorry, I don't really understand where this question gets at. There's another question. The attacker always has at least a winning probability 1/2 if they choose at random. Exactly. So the adversary can just output a random guess that just ignoring the ciphertext, right? In this experiment here, A gets this challenge ciphertext C star, and he can just ignore it and output a uniformly random bit B prime and still win with probability 1/2. What this definition captures is that no adversary can do better, right? There's a trivial dumb adversary who just outputs a random bit, independent, or even a fixed bit, always outputs 0, always guesses 0. And this adversary is as good as any other conceivable adversary. That's what this definition says. But to get, so there's another question, but to get 1/2 probability through random guesses, the adversary doesn't need to be unbounded. Does it? No, it doesn't. But what this definition says that even an unbounded adversary, an all-powerful adversary, isn't better than the dumbest possible adversary. That's the spirit of this definition. Okay, now I've given you 3 definitions, and that seems sort of bizarre, right? Why should I come up with 3 different definitions to define security for one and the same thing? For sure, one of these 3 definitions must be the best one. So who thinks that the first definition was the best one? Maybe raise your arms. Who thinks the second one was the best one, or the third one? Second, put that on quiet. Hours. Well, the thing is, all these definitions are equivalent. They all model the same thing. They only differ in the way they make this notion accessible to us, or to make this notion of perfect secrecy interpretable. If you ask me, definition 3 in a way does the best job in giving an idea what perfect secrecy actually captures. And again, as a spoiler, it is exactly this definition, definition 3, from which we will depart to define weaker notions of security, where the keys can be smaller, and where we can have encryption schemes with all kinds of extra properties. Okay, so these 3 definitions are equivalent, and yeah, that's sort of a somewhat lengthy proof. Let's see, I still have 20 minutes. Let's see how we're gonna get there. I kind of still wanted to do this today. So let's see how we get from definition 2 to definition 1. Definition 2 says for all m prime in M and C in C, we have that probability if we encrypt M to get C is the same as probability if we encrypt M prime to get C. So what this means for any message, this probability here is the same. You can take any pair of messages here. So I can define a delta C as probability, and if I encrypt some M to get C, this is the same for all messages M. Right? So this delta C just doesn't depend on M. No matter what you plug in for M, this delta C is always the same. There's one question. Does this mean that the one-time pad doesn't hold perfect secrecy according to def3 since it keeps the length of the message? That's a good point. And that's exactly the reason why we've specified a message space. Now, our message space are strings of fixed length. They're not strings of unbounded length. They're strings of fixed length. And if you have a shorter string, you need to pad it somehow, like with zeros or whatnot, to be even in the message space. So messages are always, the way we define it here, are always of the same length. Because for the one-time pad, messages are just strings of length, binary strings of length n. Okay. Now, so this is what we have from 2. Now let M be any distribution of messages. Then we want to show what we want to show in order that definition 1 holds. We have to show that let's use a different color. Color for this. Probability M equals M given enc k comma M equals C is the same as probability M equals M. All right, for all M comma C. Good. How do we do this? Well, of course, we're going to try base. So the probability that M equals M given enc k comma M, sorry, this should be a capital M here. Enc k comma M equals C is, of course, the same as probability via base. This is base. Probability enc k comma M equals C given M equals M times probability M equals M divided by probability enc k comma M equals C. Now, if I let's maybe underline this with green. If I look at this first, what is this? What is this term? Well, probability enc k comma M equals C given M equals M. Again, I can just plug in M on the left side, is just probability, excuse me, enc k comma m equals c, right? And I can drop the conditioning because I've eliminated capital M from the left side, but this is just delta C. Okay, now again, it's always the same thing with with base rule. Second, we look at this guy here. And what do we do with this? Now we still have to look at probability enc k comma m equals c. What we do there is, of course, first the law of total probability. And we write this as sum of all messages, let's call them M prime, which are in the support of this random variable M, all messages that have a non-zero probability of occurring when we're generating messages with this message distribution M. Here, probability enc k comma m equals c, given that m equals m prime times probability m equals m prime. But here, as we did with the green thing a moment ago, we can immediately see this is just delta C. Whoops. So this just becomes some delta C times m prime in support m, probability m equals m prime is delta C times some m element support m, or m equals prime. But this again, the support of m are all values which have a non-zero probability of occurrence, and if we go through all of them and sum the probabilities up, again this is just 1, right? So this term is also delta C, and from this it follows probability that m equals m given enc k comma m equals c is now just delta C times probability m equals m divided by delta C, but that's just probability m equals m, and we're good. So now we've established that definition 2 implies definition 1. Okay, let's go ahead. And next thing is we show that definition 3 implies definition 2. And the way we're going to do this is via contraposition. This is a proof technique you should have seen already quite a few times, and which happens all the time in cryptography. So the question was, can you show the last slide again? There's a question, probability m equals m prime is 1 divided by size of the message space. No, I haven't assumed that m is a uniform distribution. It's any distribution. Good. Now we do this by contraposition. And how do these proofs by contraposition work? Well, first we assume 2 does not hold, right? That is, there exist messages M comma M prime and ciphertext C, such that, let's say, probability that when we encrypt M to get C is not the same, but larger than truly larger. I mean, this would be different, but we're now just saying larger than the probability to get C. C when we encrypt M prime. Right? This is if 2 does not hold, this must be the case. We can flip the roles of M and M prime, but that's just a substitution of names. Now, our goal will be construct an adversary A such that the winning probability of this A is actually greater than 1/2, right? We said a scheme is perfectly secret if the winning probability is exactly 1/2. Now we say that if definition 2 does not hold, then definition 3 should also not hold. That's a proof via contraposition. And how do we do this? Well, how does my adversary A look? Oh, I'm running out of time quickly here. It just takes these two messages, M prime, gives them to the challenger, whereupon the challenger, of course, returns this challenge ciphertext C star. And my adversary, even though it could be unbounded, this adversary will be efficient. Just said if C star, the challenge ciphertext equals C, right? And C, that's this guy from up here. Let's maybe use colors to make this clear. M prime is the same as up there. And M is of course that one. That's what my adversary does. He takes these guys. If C star equals C, it sets B prime equals 0. Otherwise, it just chooses B prime uniformly from 0, 1 and gives back B prime. What does it say? Int A equals 1. That's a 1. That's how I write a 1. That's my 1. That's how I write a 1. Okay, now obviously the first thing is the first thing to note here, obviously, probability that C star equals C, right? That the challenge ciphertext actually is C. This is greater 0 because we know that if we encrypt M, right here. If we encrypt M, then we must have a non-zero probability of getting this ciphertext C. The question here isn't the goal to show that yeah, okay, this question has already been answered by someone in the audience. So now let's write, let's reformulate this. We can if B equals 0, right, then we're just encrypting M. Then we have the probability that if we encrypt M, I mean, this is just restated what I wrote here. This is just the same thing. I mean, this holds because ability. Let's say because this is equals C star if B equals 0. K comma M prime equals Z, and since this is a probability, it must be greater equals 0. So really, all this is now just the explanation that the probability of getting this or of having this challenge ciphertext become this value Z is greater than 0. Ooh. I spent quite a lot of time. Maybe let me put this thing here last. Probability. We in the end, we want to look at the probability that my adversary A wins this experiment, right? The probability that int A equals 1. And what we're going to do now is we're throwing at this our one of our favorite tools, namely the law of total probability via the following two events. First one is int A equals 1 conditioned on C star equals C, right? Why am I doing this? Well, I want to analyze what this how this adversary here performs, and the adversary distinguishes between cases. He has the case C star equals C and C star not equal C. So I want to analyze the success probability of the adversary in these two cases separately, and that's precisely what the law of total probability allows me to do, to carry this case analysis over into the probabilities. Star equals C and plus probability int A equals 1 C star not equals C times probability C star not equals C. But now it's the last thing. I know what happens in this case. What is this probability? What's the probability if C for the adversary to win if C star is not equal C? Can someone tell me what's happening there? I mean, here the adversary chooses B prime uniformly at random. So what's his winning probability? Exactly 1/2. So this is exactly 1/2. Now, what we need to show, right, what I'm going to have to do next time is that probability int A equals 1 given C star equals C, that this is actually greater, really greater than 1/2. But okay, I'm going to leave it with that. Our quiz is going to open in 1 minute. So please, everyone, log into the Moodle and take the quick test on today and today and Tuesday's lectures. So as requested by you, this time all the questions are displayed simultaneously. So hopefully not that many of you get 503s when trying to access the test. I'm still going to be here for a while. I'm going to stop the recording now. Please just tell me if you're having issues taking the quiz. Thanks. See you next time.